Hello. This will be a demonstration of Proposition 3 from Book 10 of Euclid's Elements, which requires us to find the greatest common measure of two commensurable magnitudes. We're given two magnitudes, AB and CD, like so. We're also given that they are commensurable with one another, so we know just right off the bat that there is a common measure between them. And what we want to find with this proposition is the greatest common measure of AB and CD. We want to find the greatest common magnitude, which measures both AB and CD. Now from the outset, we're just going to stipulate that AB is the lesser of these two magnitudes, but it really doesn't matter. CD could be the lesser, and this proposition would work all the same. Now, it is either the case that AB measures CD or it does not. If it does measure CD, then it's obviously the greatest common measure of both AB and CD. It's clearly a common measure because AB measures itself. So if it also measures CD, it is a common measure to both AB and CD. And it's also clear that there will be no greater magnitude which measures AB than AB itself. So AB, if it does measure CD, is immediately the greatest common measure between AB and CD. But if it does not measure it, then we're going to do a process like we saw in Proposition 7.2 all the way back with the number theory, where we're going to subtract the lesser of these two magnitudes from the greater until we get a remainder that is less than the subtracted magnitude. And then we're going to go back and subtract that remainder from the lesser, and we're going to continue doing this. And what we know from the fact that these two magnitudes are commensurable is that we'll eventually be left with a remainder of one of these two magnitudes, which measures the remaining magnitude before it. For if this is not the case, then this process of continuous subtraction will go on forever. But if it does go on forever, we had shown in Proposition 10.2 that the two magnitudes will therefore be incommensurable. But we were given that they are commensurable, and so we know that there will be some remaining magnitude which measures the remainder before it. Now, with that out of the way, we're going to begin this process of continuous subtraction by subtracting from CD as many times as we can AB. As I've drawn it right now, it really only looks like you can do that once. So AB is going to subtract ED out of CD, and it's going to measure ED, and it will leave CE as a remainder, which is less than itself. So what we're going to do, we're going to take this same remainder, CE, subtract it off from AB until we get a remainder that is less than CE. So let's do that. And again, it looks like I can only do it once. So CE measures FB, leaving AF less than itself. Now, we had shown in the previous step, step 2, that this process of continually subtracting the lesser from the greater cannot go on forever. And so we know that at some point, the remaining magnitude will measure the remainder before it. And Euclid stops the buck right here and says, okay, AF is going to measure CE, but it won't always stop at the second time. Sometimes you'll have to do it like 3 or 4, maybe even 5 or 6 times, or God forbid, 7 or more. But the point is, you'll eventually be left with some remainder like AF, which measures the remainder before it, which in this case is CE. Now, what we want to show is that AF is that magnitude which we sought to find. It is the greatest common measure of AB and CD. That's going to involve 2 steps. That's going to involve first proving that it measures both AB and CD, and second, that it is the greatest such magnitude which measures both AB and CD, that there is no magnitude greater than AF which measures both AB and CD. As for the first, proving that AF is a common measure at all, we know that AF measures CE, and CE also measures FB. We get all of that from our third step. And so what a property of magnitudes tells us is that because AF measures CE and CE also measures FB, that AF therefore measures FB as well. But it clearly also measures itself. So AF is also going to measure the sum of AF and FB, which is just the magnitude AB. We can see that quite clearly. So AF measures AB. But we also know that AB measures ED. So again, by that same property of magnitudes, AF is also going to measure ED. But we had set it out in our third step as well that AF measures CE as well. So therefore, AF is going to measure the sum of CE and ED, which is clearly just the whole magnitude CD. So AF has been shown to measure CD. But we had also just shown that it measures the magnitude AF, so AB rather. So therefore, AF is a common measure of AB and CD. Now, I also say that it is the greatest such common measure that there is no magnitude greater than AF, which measures both AB and CD. For if there were, let us call such a magnitude G. G will be greater than AF, and it will also be a common measure of AB and CD. It's going to measure both AB and CD. Now, we know that G measures AB. We have just shown that. And we have also shown that AB measures ED. We had set ED out in such a way in our third step. So therefore, by a property of magnitudes, G is going to measure ED. But we had also set out G such that it measures the whole magnitude, CD. So therefore, G will also measure the difference of CD from ED, which is just the remainder CE. So G measures CE. But we also know that CE measures FB. So therefore, again, by that same property of magnitudes, G is going to measure FB. But again, it measures the whole magnitude AB. So it's therefore going to measure the remainder of the greater over the lesser. So G is going to measure AB minus FB, which is clearly AF. So G is going to measure AF. And because G measures AF, it is therefore less than AF. It is not possible for a greater magnitude to measure a lesser one. But we had set out G to be greater than AF. So what we find is that in our sixth step, G is greater than AF. But in our eighth step, G is less than AF. So the same magnitude G is both greater than and less than the same magnitude AF, which is obviously absurd. It is impossible. And so we can conclude that there is no magnitude greater than AF, which measures both AB and CD, which means, therefore, that we have found the greatest common measure of AB and CD to be the magnitude AF, which is what we set out to find. So we are therefore done with the proposition QEF. As a final note, there is a porism appended to this proposition that states that if a magnitude measures two magnitudes, it will also measure their greatest common measure. We get this from our eighth step here, wherein we showed that G, because it measures AB and CD, it also measures AF, which is their greatest common measure. So that's where this porism comes from. You'll of course notice, or maybe not of course, but the astute among you will recognize that this proposition is quite similar to proposition 7.2. I had already mentioned it earlier in the video, but just to make it explicit, this is the equivalent proposition, but for magnitudes. Remember that 7.2 was about finding the greatest common measure of two numbers, and that's what this proposition is about. But instead of numbers, we are finding the greatest common measure of two commensurable magnitudes. But other than that, the proposition is much the same. In fact, the way we get the greatest common measure is the same, and the process by which we prove that it's the greatest common measure is identical. So hopefully this proposition wasn't too hard to follow. That's all I've got to say about this proposition, so I'll end the video here and move on to proposition 10.4.